Hello, hello, hello. So we're getting close to done. One of the last things we need to talk about is the way that coils act when they're in electrical circuits. So what I have here is let me get my little pointer. What I have here is a power supply and a switch and a coil, which happens to be wrapped around a piece of iron just to magnify any kind of magnetic effects. But the main point is that you have this coil. So the question arises, what happens when you throw the switch? And you know from Lenz's law what happens. What's going to happen is that the current is going to attempt to establish itself, and you're going to get an induced EMF that's going to end up fighting that. So if you lay your hand down on the coil, your right hand on the coil in the direction that the current would like to flow, you can figure out the direction of the magnetic field down the axis of the coil. So it's going to end up being off to the left here. And I think the graphic shows it. And so this is the direction of the quote unquote external magnetic field down the axis. The flux is increasing, which means this coil is going to attempt to set up a current that will produce a magnetic field in the opposite direction. Okay. Now, what that means is that the magnetic flux down this axis is not going to end up increasing as fast as it would. I mean, that's basically the bottom line of the whole thing. But what's really important is that right at the beginning, when the change in flux is really quite radical, the induced EMF is going to be large enough to produce this reverse current that is going to end up nulling out the current that the power supply is attempting to generate. And what's going to happen is that initially you're going to get no current at all. So let me get rid of this so you can see. You get no current at all. And what will happen is that very slowly current will start trickling through the system, and you'll get more and more and more and more current. And the change in the magnetic flux, the change in this external magnetic field will happen more and more and more slowly. The change in magnetic flux will occur more slowly. The induced EMF will get smaller and smaller and smaller. The effect will get smaller and smaller and smaller. And sooner or later, you will get to the place where the current will basically just be steady state because there will no longer be a changing magnetic flux down the axis. And so that's what a coil does in a circuit. You flip the switch, you don't get current to start with. Very slowly, the current begins to grow. And in fact, there is a time constant associated with this thing. Okay, there is some amount of time that it takes for the current to end up rising up 63%, and we will derive what that time constant is here shortly. So this is the symbol for a coil. You may very well want to know what the induced EMF actually is across this coil, especially if you try to use Kirchhoff's law on this thing. You want to know what the voltage change was across the element. The only relationship that we have for the EMF is this, Faraday's law. The problem with this is that to be able to execute it for something like a coil, which is actually a little circuit element, is that you'd need to know what the cross-sectional area of the little circuit element was, and you'd need to know how the magnetic field was changing down the axis. And all of this is stuff that would not be easy to measure. And so at some point in time, somebody realized or noticed that what's really changing the magnetic flux and basically changing or producing the EMF was the fact that the current through the coil was changing. So they suggested that the EMF was actually proportional to minus the change in the current. For this to be made into an equality, you need a proportionality constant, and that proportionality constant is what's called the inductance of the coil. And so this is Faraday's law for a coil. The induced EMF equals minus the inductance of the coil times the rate at which the current changes with time. Inductance has the units of henries, although 1 Henry inductor is a huge inductor. They're usually in millihenries. Couple of observations, just off the wall observations. When we're talking about resistors, note that we said the voltage across resistor equaled the current through, and the proportionality constant was its resistance. And that was the thing, that proportionality constant was the thing that told you how big, quote unquote, the resistor was. We were talking about capacitors. We said the charge on one plate was proportional to the voltage across the plates. Proportionality constant there was C, the capacitance of the capacitor. And that was the thing that told you how big, quote unquote, the capacitor was. Now we're looking at an induced EMF across the leads of an inductor, or the leads of a coil, being related to, proportional to, the rate at which the current changes with time. Turns out inductance is that proportionality constant. Inductance is the thing that tells you how big the coil is. And then this is just mentioning the millihenry thing. So this is just interesting. The parameters that we use to tell you the size of the elements, they're all proportionality constants relating one quantity and another quantity that is having to do with it's kind of the physical characteristics of the entity that we're dealing with, which is interesting. Different things that coils are called. They're obviously called coils. In electrical circuits, when you're actually talking about the elements, they're sometimes called solenoids. A lot of times you'll hear them called inductors, which is probably what you'll hear me call them most of the time. If you run into an old timer, the geezers used to call them chokes. Just stop, something to know. Minor point. Inductors have they're made out of wire, which means they have resistor-like resistance to them. So you will see coils in circuits where you'll have an L value, but you'll also have a resistance value. And normally it's a little r sub L. That little L is not for load. Okay, so oftentimes you will see a resistor in a circuit and it says R sub L. That L is identifying the load. It's called the load resistor. It's the thing that is dissipating the energy. It's the heater that's warming up, or the light bulb that's giving off light, or whatever. It's the load. Okay, this L is associated with the inductance L. Okay, and it's like an internal resistance associated with the inductor, and you will see that value given. Sometimes they just let you assume that it's zero and you can ignore it. Very quickly, if you remember back with capacitors, you had a parallel plate capacitor and you were asked to figure out what the capacitance was in terms of the parameters of the capacitor. And so you derived that, C was equal to epsilon naught A over D. If you remember the way that you did that, you started with the fact that the capacitor, or the capacitance, was equal to the amount of charge on one plate divided by the voltage across the plates. And to figure out the voltage across the plates, you had to use Gauss's law to figure out what the electric field was in between the plates. And then you had to use that relationship that said the voltage difference across the plates was equal to the integral of E dot dr to figure out delta V. And then you put the delta V in, divided it into Q. The Q's canceled out. You got this relationship for C. Okay, there's a similar way of doing, or there is a similar problem for inductors. Okay, you have some geometry. You want to know the inductance of the geometry. And the technique basically is that you're going to go ahead and you're going to use minus N dV dt, Faraday's law, equaling minus L di dt. And you'll notice there's an L in there, an inductance value. And so you have to figure out what the flux is. You take the derivative of the flux. That's the dV dt part. And you just fuss with the relationship. And by the time you get done, you have an expression for L. And so this is an example. So very quickly, there is the flux through the cross-section of that coil. If you want to look at this more closely, you can. Just freeze the video. Here is the L di dt equaling N dP dt. And you will notice that when you get to, I lost my little You'll notice that when you get down here, you have to multiply both sides by dt so you can integrate. By the time you get done, you end up with this nice little relationship. The i's, when you go ahead and put in for phi, the i's cancel out, doink, doink, and you get this nice little relationship for L. The little added twist to this whole thing is that little n is defined as the number of wines per unit length, and you have an n over L quantity here, so you can get rid of that. And pi r squared times L is the volume of this cylinder. This is a cylindrical solenoid. And so if you fuss with the math, you can basically get this relationship down to simply mu naught times the number of wines per unit length squared times the volume of the entity, which is kind of going overboard with the math, but that's life. Okay, so here's a relatively typical question. For the circuit to the right, notice that the switch is thrown at t equal to 0. What's the initial current in the circuit just after the switch is thrown? Go ahead and pause, think for a second, come up with an answer, and then come back. Okay, you should be back. Hopefully what you did was you thought through this and thought, okay, so that back EMF is going to end up getting generated. It's going to fight the buildup. The initial current's going to be 0. By the way, I didn't mention this before, but this induced EMF that's set up that fights the increase in the current, it's called a back EMF. Okay, I mean, it's an induced EMF, but it's actually called a back EMF by the geezers. What is the current in the circuit after a really long period of time? Pause, think, come back when you're ready. Hopefully you're back. Okay, so after a long period of time, the magnetic field is no longer changing. There's no longer an induced EMF. So this is just like a circuit that's got this amount of resistance and this amount of resistance in it. So it's just like a normal old steady state circuit with resistance in it. And so there's the math. And I wish I could get rid of this. Is just V naught over the effective resistance. Write a differential equation that characterizes the current as a function of time. So this is a Kirchhoff problem. So you have a voltage increase here. You have a voltage drop across here of minus L di dt. Okay, that's the induced EMF. Minus I times little r sub L, because that's the Ohm's law-like voltage drop across here, minus I times capital R equaling 0. So there that thing is. You've seen an equation that's similar to this when we were doing a capacitor and a resistor in a circuit like this. You ended up seeing an equation look like that. And we actually solved it. And by the time we got done, you had natural logs and you had exponential solutions. And in fact, the solution came out to be looking something like this. Here's all of the math. If you want to go through it, you don't necessarily have to, but you should be able to write out that equation, or at least that equation anyway. Notice here in the capacitor situation, you had e to the minus t over RC, and RC ended up being that time constant. So 1 over whatever's in this slot is the time constant. Apparently the time constant for this monster is L over R net. Asked what the time constant is, L over R net. What does it tell you? Okay, it tells you the amount of time that it takes for this current to get up to 63% of its maximum. If the current has been flowing for a long time and you open the switch, what's going to happen? Well, the same thing that's going to happen is when you threw the switch. Okay, an induced EMF is going to end up setting itself up. It's going to fight the change in the coil. So current's going to continue to flow. It isn't just going to drop like a rock. It's going to continue to flow for a short time, and then it's going to start to drop out gently. And so by the time you get all done, you're going to end up having something like this. Throw the switch, it builds up to steady state. Open the switch, it drops out slowly. One time constant, 63%, two time constants, 87%. from where you threw it. One-time constant drops you down to 37, so you've lost 63%, etc. Okay. So this is just another problem. It has numbers. If you want to go into the PowerPoints and look at it, you can. I'm going to skip over it just for time considerations. So the last thing we need to do is talk about energy wrapped up in an inductor. So if you remember capacitors, the energy was wrapped up in the electric field between the plates. So if you just think about it, you would expect that the energy wrapped up in an inductor would be where? Okay, it's going to be wrapped up in the magnetic field down the axis. Okay, so if you write out Kirchhoff's law, and this is pretty much what we did as I remember for the capacitor, write out Kirchhoff's law for this circuit, and then multiply I all the way through, you end up with this term being the amount of power that's being provided by the battery, this term, which is the amount of energy that's being dissipated by the resistor, which means apparently this term must be the amount of energy that's being dissipated by the inductor in the circuit. If this is the amount of energy being dissipated by the inductor, then the power involved in storage must be the opposite of that. If you additionally notice that the power is the change in work with time, which is minus the change in the potential energy of the system with time, and you combine this and that, and you take this little gem and stick it in there and fuss with the math, lo and behold, you get this relationship for what the potential energy of a charge or a current carrying inductor happens to be. And obviously it's 5 o'clock. You can tell from my grandmother clock. And this is the relationship for figuring out how much energy there is wrapped up in a current carrying inductor, where I is the amount of current that's flowing. So that's it. I've talked as fast as my little brain would allow. Hopefully you're listening to this thing at 1.5 times speed, so it's like I'm really flying along. If there's anything that you needed to go back and look at more closely, you can do that, or you could just take a look at the PowerPoint slides that you have available online. So anyway, that's it. Keep smiling, folks. Life could be worse.